And what that resistor does is it slows down the amount of current that can rush to the short to the point where it doesn't heat the cell up to go into runaway. And so one of the things we're the most proud of is shipping real commercial cells out of an automated factory. At scale, we believe our cell will actually be lower cost on a per watt hour basis than a traditional lithium ion battery. You know, our first product is at 900 watt hours per liter. Cycle life, you know, well beyond 1500 cycles, above I think still 90% when where those cells are going. You know, our cells, you know, they're more than 30 times higher conductivity than a traditional cell. And so that allows you to pull that heat out of the cell much more efficiently in the thermal management system of the car.
Well, I'm excited to introduce today Cameron Dales, who is the Chief Commercial Officer at Enovics. And it's an exciting company that is commercializing right now batteries for smaller devices, but they hope to in the future commercialize batteries for electric vehicles. And it's not just any battery, it actually is what they call a 3D architecture and silicon anode battery. So we're going to talk all about this technology. But before we do that, Cameron, could you tell us a little bit about your role at Enovix and also your professional background as we dive into this exciting topic?
Sure, John. Yeah, thanks very much for having me. So I'm the Chief Commercial Officer at Enovics. We're an advanced battery company, and as you mentioned, we have a different way of constructing and architecting the cell, and hopefully we'll talk a little bit about that going forward. So my role here is I primarily take care of all the external functions of the company. So I work with our customers. I have marketing that my team does. I work with investors, some partners, those sorts of things. My background is in engineering. I'm a mechanical engineer by training. I started my career actually at Lockheed Missiles and Space Company down in Sunnyvale, California, kind of down the street from us. I worked on some of the first commercial imaging satellites. So, you know, as you see Google Earth imagery and, you know, what's going on in the Ukraine, for instance, you know, a lot of that technology of essentially Earth observation satellites used for commercial purposes. That was my early part of my career. And then I went to a company called Symix Technologies after that, which was a startup working on material science and essentially automated robotic lines for synthesizing and discovering new materials. And that's where I got interested in doing startups. And from there, after about 10 years, came to Enovics to work on energy storage and you know, really one of the really truly unsolved big problems in the world, which is how do you store energy? How do you carry it with you personally or in your vehicle, and essentially you know, live life unplugged. So that's what I've been doing for the last 14 years, and it's been quite a journey here at Enovics. We started the company back in 2000, let's call it 2007, and have been through, you know, the long R&D wars of new battery technology. These are not simple technologies. It take a long time to you know, to have them meet all the different attributes of a product that can actually be used by real customers. You know, we took the company public a couple of years ago, have built our first factory here in Fremont. We're kind of across the freeway from Tesla's first big plant, and started shipping commercial batteries to customers middle of this year. And, you know, we expect to see some of those products on the market next year. And that's kind of the journey that I've been on over the last few years.
It's awesome. That's a very exciting journey, and you have a good diverse background. And definitely, I see why you're drawn to the energy sector and battery technology in general. It's really, there's a great revolution going on right now, and there's still a lot to solve. You know, a lot of technologies that we live with today, it's just very small incremental changes. But I think there are huge changes coming with battery technology, and Enovix is really doing some work towards that, as we're going to talk about. So with that being said, let's move right into the battery technology itself, specifically diving into the 3D silicon cell architecture. So that's unique. That's a marketing term, obviously, the 3D silicon, but it's not just a marketing term that means nothing. There's actually a 3D architecture that we're going to talk about here. So could you talk about that architecture, introduce us to that, and then also talk about how that compares to how a traditional lithium ion battery is manufactured?
Sure. Yeah, love to. So yeah, you're right. What is a 3D cell or 3D architecture? It's really an attempt to try and describe a different way of constructing the cell. So the anodes and the cathodes and the separators within a battery cell. And traditional batteries have been made the same way literally for over 100 years. And there's essentially the active materials are coated onto the current collector, which is essentially an aluminum foil layer or a copper foil layer for the anode. Put an insulating layer between the two, called a separator, and then roll it up and put it in a can. And that's called a jelly roll architecture. That's how 18650, 2170, and 4680 cells are made for Tesla. It's typically how cells are made for the cell phone that's probably in your pocket today. It's not rolled into a can, but it's rolled up around a mandrel and squished down and put into the battery form factor that fits in your phone. So people have been making cells for a long time, and most of the progress in the battery industry has come out of material science improvements. A little bit better cathode, a little higher voltage. Maybe it's a different chemistry system. Once every 20 years, you'll see a transition. And not very many people had really thought about, well, maybe there's a better way to manufacture and design the cell rather than what Volta did hundreds of years ago. And then Sony continued to do when they introduced the lithium ion battery in 1991, maybe because it's similar production technology as to what they were already in production on, essentially coating films. And if you think about where Sony came from, their audio tape business and ultimately their video recording business were coated films that were rolled up into rolled architectures. And so when we started the company, we thought, well, maybe there's a better way to do this. And our founders came from places like IBM, that was very much in the mix and was one of the inventors of the hard disk drive, and developed all sorts of different techniques for manufacturing three-dimensional small parts that could be manufactured at massive scale and incredibly low cost. And so there was that type of three-dimensional thinking that led to this idea of structuring the battery cell in a different way. And really what it comes down to is, instead of having one anode and cathode and rolling it up, or a few very large sheets of anode cathodes and stacking them up, what if you broke the electrodes themselves into dozens or even hundreds of different layers and connect them in parallel in kind of an interdigitated comb structure, which is how our cells are put together and interconnected electrically. And then you're kind of stacking them in the long axis. And that leads to a number of really interesting different capabilities of the battery that are really not coming from the chemistry at all. It's really coming from the cell architecture. It allows us to use some different materials. You mentioned silicon in the anode, and if your audience isn't familiar with the deep technical work that's being done on materials, most batteries today are currently made out of graphite or carbon, and in the anode side, the negative electrode. But the next kind of generation in anodes, it looks like it's going to be the material silicon, which has some tremendous properties in terms of storing more lithium ions. Theoretically up to 10 times as much in the same amount of material. But it has some very big challenges in when it accepts the lithium. It expands in volume. It has some efficiency issues that you need to get over. And so this architecture has allowed us to use some of these materials that have big volume changes. And it also allows for some quite interesting cell design architectures that improve the safety of the lithium ion battery cell, which of course is a big issue, right? In terms of how do you prevent these batteries from going into thermal runaway if there's an internal problem in the cell and creating a fire. And so when you do things a little bit differently in terms of the cell design, it opens up, quite interesting and different potential benefits in the end product.
you kind of introduced two topics that I definitely want to dive into. That first one is talking about how this 3D architecture allows you to have a silicon anode. And from what I read on your website, we're talking about 100% active silicon anode. You know, we talk about like a Panasonic 2170 battery, you may be talking about maximum 5% silicon from what I know. Maybe, maybe less, but somewhere around 5% is probably a number I've seen thrown out there. Whereas we're talking about here 100% active silicon anode. So talk about how this architecture, how does this architecture, you've described it very well, and I'll put up pictures from your website of what that looks like for the audience. But you described it well, but how does it exactly interact, and how does it limit the expansion of silicon in the anode?
Right. It's a great question. And, you know, you point out one of the key challenges with silicon is that when you charge a silicon anode up, it goes through, the first time you do that, it goes through a phase change in the material, which causes a volume expansion in the material. So it's not exactly the same, but kind of an analogy is, you know, if you freeze water and it turns into ice, you know, it changes volume and you break your milk bottle if you leave it out, if you grew up in northern Michigan or something like that. So it's analogous to that, and really there's no practical way to contain that volume expansion. That volume expansion is material property. It you know, is gigapascals of pressure that's created. The only thing you can really do is try to manage that expansion. And if you just put a silicon anode in a regular battery, it'll you know, dramatically expand the battery cell itself, swell up, and ultimately the particles themselves will come off and crack, and it'll lose its charge after, you know, a handful of cycles of charge discharge. And so the question is, how can you manage that process so that you can have a practical functioning battery? In our case, what we do is we use fairly straightforward, you know, standard silicon materials. In our first product is silicon oxide. It's essentially the same material that goes into, you know, Panasonic cell at 5%. We're just using 100% of it. The reason we're doing that, of course, is because you can get a lot more energy in the anode and shrink the size of it, and therefore have a higher energy density battery. And what the architecture allows us to do is, in this stacked, design, is we build in a certain amount of space inside the cell, both in terms of how the layers are stacked, but then also in terms of the porosities, for instance, of the materials inside. And then we put what we call a constraint system around the stack, and it's a very thin, and maybe it adds 2% additional kind of volume to the overall cell, and that essentially holds that stack together at the right spacing. And then when we charge the silicon for the first time, it expands, as it of course must do from a material perspective, to a designed point of pressure or stress on the cell, and then that constraint basically holds it together and puts stack pressure on the stack. And so what's the reason for doing this? The first is that you need to hold the stack together and get it to the right kind of density on the inside, so it's a mechanical function. The second is, it turns out if you put stack pressure on the electrodes, and you can then maintain electrical connection to all the silicon particles as they expand and contract in cycling, that's really the key to achieving, you know, commercially relevant cycle life. So everything stays connected, everything stays, you know, electrically performing the way it's designed, and you avoid these failure modes that typically people have seen with silicon anodes. And so there's a trick we play in the architecture for this stack pressure, and you can imagine if you had a cell, this is a cell phone cell that we make. So, you know, battery cell, EV cell would be larger than this even. But if your electrodes were stacked this way, there's a full face of the area of the cell that the pressure is acting on. And since pressure is equal to force times area, if your area is large, that pressure creates a big force, like on the order of a couple of tons of force. It's not practical to hold that back with some sort of constraint system. Now, in our cell, we stack the cells on the thin axis, and so the area there that pressure is acting on is quite small, and so the force that the silicon is trying to push, on the stack, is able to be constrained essentially, or limited, by, a constraint system that is really basically like a metal foil. So it's very low overhead, and it ultimately allows you to practically have a mobile device, in this case for something for, like a phone, but also a mobile device like a car.
That's a really cool way to look at the problem, and I like what you described there. I think that's very easy to understand. It's also interesting, you talked about only an extra 2% volume for the casing, and when you talk about how much you gain with adding silicon, that's just, it doesn't even matter. An extra 2% doesn't even matter at that point, because you gain so much by adding silicon. So even if you had to add an extra 10 or 20%, you would still be way ahead with silicon. So that's really interesting. I think it's exciting. We'll talk about energy density in a minute, but you also, so thank you for covering that, how it limits the silicon expansion, or really it doesn't limit it, but it works with the silicon expansion. Would be a better way to describe that.
Accommodates it. Yep.
Exactly. Because you're not going to change the laws of physics, but you can engineer around them. You've done that there. But can you talk about, so you talked about safety and limiting thermal runaway. Can you talk about your BrakeFlow technology? Yes. And what that means for safety, and talk about the nail penetration tests of your cells.
Yes. So thanks for bringing that up. I mean, this is an incredibly exciting development that, we started to share with the world over this last year. And in fact, there's a really cool video that, if people are interested in learning more about this, our chairman, TJ Rogers, who's kind of a legendary Silicon Valley character, puts on, the lab coat and goes to the lab and blows up a bunch of batteries and talks about BrakeFlow. So it takes a little commitment. I think it's, 20-25 minutes long, but I think it's well worth it for people who are interested. So what is this BrakeFlow technology? This is another example of, if you're going to try and do something differently, in our case, this cell architecture, it opens up all sorts of different possibilities for the product that you wouldn't be able to consider if you're doing it the same old way. And so in this case, I think your audience, I'm sure, is familiar with thermal runaway, lithium ion batteries catching fire, either because there's an internal defect in the cell. If you think about like the Samsung fires from a few years back, or the aircraft fires, which people forget about that, or the cars that were recalled, and the manufacturer said, please don't park these in your garage because they might spontaneously catch fire. So this is like a serious problem in the industry, and it's not unique to batteries. I think anytime you're storing energy, whether it's in the form of a gallon of gasoline or whether it's in a battery, the uncontrolled release of that energy is a big problem. And so what BrakeFlow tries to do, and I think very successfully, is it essentially allows, and I'll talk about how it does this, but it essentially allows, if there is an internal short in the battery, which is way most runaway issues happen, the root cause tends to be there's a short somehow between the anode and the cathode. And when that short happens, all the energy of the anode and the cathode rush through the short to try to get to the other side, which causes heat, which then causes the interior, the interior materials of the battery, typically the cathode actually, to get above its ignition temperature. It catches fire. It's an oxide, meaning it has oxygen in the material, so it doesn't even need oxygen from the air. And it just catches fire, and the reaction continues to burn and burn and burn and accelerate, because you've got an oxidizer in there, which is, kind of like rocket fuel, right? Solid rocket motors have an oxide material that they burn, so it's not pulling it from the air or the atmosphere, it's pulling it from itself. So this is a difficult problem to solve. Our approach here, using this 3D architecture again, is, remember, we've got all these plus minus pairs and connected in parallel along the bus, of each side, the negatives and the pluses. And what we do is, on the negative side, we put a very inexpensive layer between all of the anodes and the bus, and that creates a very small resistor there, which when the device is functioning properly, all of those resistors in parallel really do not affect the ability of the cell to discharge or charge current. But if there's a short internal to the cell, then normally all the current would like to rush through that short, just like in a regular cell. But in our case, you now have resistors on the outside, and for that current to get through that one leg of the network, it has to go through that one resistor. And what that resistor does is it slows down the amount of current that can rush to the short to the point where it doesn't heat the cell up to go into runaway. And so it's kind of like, the analogy maybe is, if you have a balloon and you poke the balloon, it pops violently if all that energy is released at the, instantaneously. But if you're able to bleed off the pressure of the balloon over a minute or two, it's a very controlled kind of reduction of the energy. And that's really what BrakeFlow does.
In a sense, it sounds like what this design allows you to do is, it's like having a bunch of little small batteries within a battery, so you can build in the safety. Is that a good way to think about it? Like a bunch of little small batteries, almost like a miniature version of a Model 3 battery pack, where you have different modules in a sense, or maybe one of those modules. If you took one of those modules out of a Model 3, you have each individual cell. If you had a resistor connected to each one of those little cells, then that could limit it. Now, that's a really cool design, and it's exciting. But a question, and we'll talk more about commercialization and stuff later on, but I did just bring up a question that I think is good to bring up now. You mentioned an expensive resistor. What, at full scale, I know you're not at full on crazy scale right now, but at full scale, what are we talking about? Like, what kind of added cost are we talking about percentage wise of a cell by adding these resistors?
Yeah, inexpensive. I mean, it's de minimis in terms of cost. There's a small amount of material cost associated with that resistor. It's a polymer that's they use it to make golf balls and stuff like that. So it's less than a penny, and so really, when you actually add in kind of the process changes to implementing this technology, probably reduces the cost of the battery overall, to be honest. And then you brought up the question of cost, which is of course massively important in any of the applications that batteries are working in, whether it's the cell phone in your pocket or whether it's electric vehicle or the grid. Cost is such an important factor, and so we've designed a manufacturing process that for the most part is identical to the way batteries are built today, particularly the supply chains. You think about the materials. We talked about silicon as an anode, but essentially we're a material agnostic company. We can use any type of cathode and typically any type of anode. We've happened to chosen the specific silicon for our initial markets in the consumer product space, but that's a variable actually in terms of our product strategy. And so given that we're very common with the whole material supply chain, as well as most of the production processes in a battery factory, we have just sort of the one piece where instead of the complicated winding tools, we have a special set of tools that we would drop in and replace that with in order to make the 3D structure. And so we're at scale. We believe our cell will actually be lower cost on a per watt hour basis than a traditional lithium ion battery. Basically getting more energy out of the infrastructure and the materials that go into producing the cell.
I appreciate you covering that. We've talked a lot about the anode side. Let's move over briefly to the cathode side, and then we'll kind of talk about some of the other technical aspects of energy density, like cycle life, etc. But let's move to the cathode. So when I looked up and researched your company, it looks like right now your test cells use a nickel manganese cobalt 622 battery cell. I think most of my audience know what that means there. In NMC 622, 6 parts nickel, 2 parts manganese, 2 parts cobalt, roughly. I'm curious that you mentioned, you're cathode agnostic. So apparently you could use a NMC 811. Could it also work well with a lithium iron phosphate technology, battery technology?
Yep. So yeah, you're absolutely right. This is really an architecture company. We've chosen it. Actually, our first products that we're making in our factory now are LCO, so lithium cobalt oxide, which has more cobalt in it. It's more expensive but higher energy than NMC, but it's the cathode of choice for the consumer product industry. So almost all consumer mobile products use LCO because of the energy density. So that's what our first products have. You referenced some NMC 622 data that we've published. This is part of a Department of Energy grant that we're working on, which was designed to show, prove that you could use our 3D architecture in chemistry systems that are relevant for the EV space. And so we chose, actually, the DOE really encouraged us to use NMC 622, which is a pretty not cutting edge, kind of standard NMC cathode, specifically so that there's no issues around the cathode side, because the goal of the program was to prove that the architecture works and that the silicon anode works, right? Which is probably the newer cutting edge stuff. And so that's why we've published a bunch of data with that. We've gotten, I think, really quite exceptional results. Cycle life, well beyond 1,500 cycles, above, I think, still 90% when where those cells are going. Exceptional calendar life, which is, maybe this is something that the broader population who are interested in batteries don't focus on all the time. People think about cycle life, how many times can you charge, discharge? But it turns out one of the most significant problems that is typically been unsolved in the vehicle space is calendar life, meaning you charge up your cell, you put it on the shelf or let it sit in your car. It's got to not lose significant amount of energy over 10 years. And most of the concepts that are out there in advanced batteries, they have a hard time passing these requirements. So we're pretty proud of some of the results. They're still early. We're about 1.5 years into the program, but very encouraged with it. So that's a long answer of what we've done. Certainly 811 is probably where the industry is going, at least for high energy cells. We haven't built 811 cells with architecture, but there's no reason we couldn't. And similarly, you brought up LFP, iron phosphate chemistries, which have some advantages, particularly in cost, relative to the high nickel and high cobalt chemistries. And we think that's quite an interesting material as well, because you could pair a low cost but lower energy density cathode with a nominal cost silicon anode architecture and get a cell that has better performance than state of the art, but not the best, at a lower cost point. So we feel that our architectural approach gives the end customers, in this case these would be automotive OEMs, a lot of flexibility in the types of chemistry systems that they want to optimize for their particular vehicle strategy. And it's definitely not a monolithic battery strategy within the automotive space. If you're building a high performance sports car, you will make different choices on batteries than if you're making a kind of a city commuter car. And so having that flexibility from a design perspective, we think is an important feature.
Obviously the high energy dense cells, I get excited about that, but I'm especially excited about the potential of pairing your technology with a lithium iron phosphate battery. Like you said, you could have a lithium iron phosphate battery with your silicon 3D technology, and you could potentially have a battery that actually beats the batteries that are out today on the market, but is lower cost. And then, of course, you could sell your technology and build other cells that are, above that. But to be able to beat current cells with a lower cost and potentially even safer than the existing stuff is really exciting. So it's exciting to know that works. Let's move over to energy density. So obviously you have the potential for huge energy density increases with your silicon anodes. Yep. We know that, but what kind of energy density numbers are you achieving right now with your test cells? What do you see in the future? And then if you could clarify, is this the lithium cobalt oxide numbers that we're talking about? What are we talking about when we talk about these energy density numbers?
Right. So, if you go onto our website, you can see kind of the specs for a range of different products. And, one of the things to really keep in mind when anybody is quoting energy density, it's quite difficult to compare apples to apples. And part of the reason for that is that different battery cell sizes, if you take the calipers to them and measure the capacity and calculate energy density, they will have different absolute value numbers. And that's just basically because if you have a large cell has a certain amount of overhead around packaging and things like that. And then as you shrink that cell down, that overhead stays roughly the same, but the amount of capacity goes down and down and down to the point where if you like made it zero capacity, you would still have all that overhead there, right? And so small batteries have lower absolute values of energy density than large batteries. So what we've done is we take essentially a standard size cell in our initial markets here, the consumer markets. There's no real standard, but we try to index all of our numbers to a specific form factor. And it's kind of a large cell phone or laptop size cell. And our first product is at 900 watt hours per liter, which relative to the industry, maybe the industry is at 700, maybe 720, something like that. So it's a step change improvement in performance in energy density. Our first products on the market though are smaller products. So I have some cells here. This is a cell that goes into a smartwatch wearable product. The absolute value of the energy density is in the let's say it's in the 700 range, whereas the industry is maybe more in the 500, 450 range, right? Here's another form factor, kind of looks like a stick of Trident gum. Why would you need a battery like this? Well, you can think of industries where AR and VR are becoming more and more important, and of course, to realize some of these mobile products of the future, the battery and power budget is probably the number one issue, or certainly one of the top issues. And so having a step change improvement in battery performance, it's really one of the enabling technologies for these future devices. And that we have a roadmap over a few years where we think we can improve energy above and beyond kind of what the rest of the industry does by materials, by architectural improvements and silicon anode improvements, and so that that performance improvement goes up. I think we have a roadmap that goes above 1,200 watt hours per liter over a few years. We just recently announced kind of our next generation of product will be in the greater than 960 watt hours per liter. We've demonstrated cells that perform quite well in the lab at that point, and then have kind of lab plans to continue to push that forward.
So you've mentioned volumetric energy density. Do you have any gravimetric energy density numbers that you can share? Because obviously volumetric is super important, and maybe even more important in your current commercial space when it comes to cell phones and stuff. But when we move to EVs, gravimetric is extremely important as well. Do you have any numbers to share on that?
Yeah, so they're roughly the same. There may be a little bit less of a percentage improvement than volumetric, but it's still a big improvement. Interestingly enough, though, I would say it's probably a point of misunderstanding in the industry that even in the EV space, volumetric energy density is definitely way more important than gravimetric. And the reason why is the following: if you think about if you're designing a car, how much does it cost you to drop the weight of the car by, let's say 100 pounds? And it's just almost always way cheaper to change the hood from steel to aluminum, or do something on the wheel wells, or these sorts of things tend to be a much lower cost way of cutting weight, as opposed to investing in advanced batteries. Whereas there's only a certain amount of volume in the car chassis to get the range that you want. And particularly as these chassis go to these, kind of skateboard type approaches where you've got this low profile battery pack that runs the floor of the car, getting to that low profile is a direct correlation to the energy density of the batteries to be able to hit the range. And so the feedback we have from the OEMs is that volumetric is way, way more important than gravimetric. The industry tends to quote gravimetric all the time, and we have always been confused by this. In fact, we were talking with our colleagues at the DOE of why do people keep quoting gravimetric energy density? It doesn't really matter. And the answer is it's historical, because in previous generations of batteries, they were 100% correlated. So volumetric and gravimetric were kind of the same. That's not true anymore. As you think of materials that change volume, like silicon or next generation things like lithium metal, those things start to diverge. And it becomes much more difficult to actually hit the volumetric side. And so why not quote volumetric? It kind of gets back to the preamble that we had on energy density in the first place. Is it's just very difficult to, in a very consistent way, compare company A and company B and battery C in a volumetric space, because it's, how do you measure it? How hard do you squeeze it? All this kind of stuff matters. Whereas on the weight side, you just put it on the scale, like there's no way to, make a mistake there, but it's probably not the most important parameter, to be honest.
Well, I appreciate that perspective because, yeah, I'm on the consumer end in a sense, and of course, I would call myself an analyst. I'm reading this stuff all day, but gravimetrics seems to be the number, like you said, that everyone shouts out.
Exactly.
But it's interesting to hear from your point of view, from the manufacturer and talking to OEMs, that volumetric more important. Interesting.
Yep.
This might be too early to ask this follow-up question based on this, but with the way it's designed, with the 3D architecture, does it give the battery better thermal characteristics? Meaning, in the future, based on what you know right now, you haven't probably tested this yet, but when you put this into a battery pack, will the cooling requirements be equal to an EV that's currently out, or could you maybe even have less cooling requirements and better thermal characteristics of these battery cells? What do you think on that?
Yeah, no, this is a great point, and this is something that we've learned over the last couple of years as we've engaged more seriously in the EV space. Of course, the initial markets for this company are on consumer products. It's a great place to have a new technology. It allows us to make money outside, right out of the gate, and become, an at scale and at cost manufacturing company without, doing a frontal assault on one of the most cost competitive markets in the world, which is automotive. But interestingly, in consumer, energy density, volumetric energy density is the most important consideration by far in the battery. A smartphone manufacturer will give their left arm for 10 watt-hours per liter. In the car space, by contrast, energy density certainly is important. You'd like to get more range, as long as it didn't cost any more. But the parameter that I think is equally important, maybe even more important, is the ability to do fast charging. So what if you could charge your car in 5 minutes at the charging gas station, rather than dealing with range anxiety and all this kind of stuff? It's a game changer for adoption in the EV space. And it turns out, to get to your point on thermal, that one factor limiting how fast you can charge, at least at the vehicle side, there's a whole other question around, can the grid support it and this sort of thing. But on the vehicle side is how fast can the battery chemistry accommodate, lithium transporting to the anode, which is, that's charging. Silicon has an advantage there versus carbon. But, once you get to a certain level of charging speed, it's not really the cell that is limiting the charge rate, in a sense, because the faster you charge, the more the cell heats up thermally. You can experience this when you put your phone on the charger, and you can feel it warming up. This becomes the limiting factor in a vehicle for how fast you can charge. And you can think of it this way: as if you've got a large EV battery, call it a 4680, it's like a can of Coke or something, and you charge that thing, it's heating the cell up all the way through that cell. And in the center of the cell, you're heating it up as well, and you've got to get the temperature of that cell so that it doesn't go so high that it cooks the cathode. And so how do you do that? You do that with the cooling system of the overall pack and of the vehicle. But the limiting factor is how quickly can you get the heat out of the center of the cell and into the cooling system. And so one of the, let's call it, unforeseen advantages of this three-dimensional architecture, and we didn't design it for this reason, but it turns out it's kind of built like a heat fin. And you have all of these electrodes with a very short path length, and a regular cell, again, if you look at let's assume there's a larger cell, the thermal conductivity of this it's much better in the long direction with the short face. And it's terrible in terms of into the big face. But of course, from a cooling perspective, you'd like to cool the big face and have the short distance. And a regular cell is designed the opposite way, because the layers of the cell are essentially insulators except for the metal. The metal's going this way. In our case, we got the metal going this way, right? And then we've got the big face for cooling in the most optimum efficient way to get the heat out. And so, our cells, they're more than 30 times higher conductivity than a traditional cell. And so that allows you to pull that heat out of the cell much more efficiently in the thermal management system of the car. And it has implications for the temperature you run the coolant at. You can run it at a higher temperature, which is more efficient to then cool it through the radiator. You can make smaller radiators. You can make smaller, fewer cold plates in the pack. So there's all these sort of system knockoff effects, which if you kind of boil it back down, all come from a fundamental parameter of the cell, which is what's the thermal conductivity and how fast can you get the heat out of the cell without cooking it. And so it may turn out that this is more important in the EV space, this parameter, even than energy density and silicon anodes and all this kind of stuff. It's an architectural improvement to allow really, really high fast charge rates and reduce system cost around the thermal management system.
Yeah, that sounds very, very promising. That's actually really exciting to hear. Well, let's go back to calendar life and cycle life. So you briefly talked about that. You had mentioned 1,500 cycles and a 90% capacity retention, which of course is insanely impressive. I think the current 2170 batteries, Elon Musk tweeted out like 2 or 3 years ago that they're good for 1,500 cycles. So obviously that's kind of the standard there. But if you're still at 90% at 1,500 cycles, that's very impressive. Now, I imagine that's not 1,500 fast charging cycles, though. That's just 1,500 slower cycles, correct?
Yep. Yeah. So, any battery, when you subject it to fast charge, will degrade more quickly. I don't have the numbers off the top of my head, but I think we just recently presented some data at the Advanced Automotive Battery Conference in San Diego, maybe last week, where we showed some data on fast charge cycle life, which definitely beats what the industry requirement is. I can't remember the numbers off the top of my head, but it's in the 500 cycles, something like that. And typically when you test this stuff in the lab, you're running every cycle max C rate or charge and discharge rate, and that's not the way that typical users would use the battery. And so depending on specific customers, they'll have protocols where every 4th or every 5th cycle is a fast charge cycle, et cetera, et cetera. So we're at the beginning of that, but it sure looks today as if we're going to be in pretty good shape there.
Yeah, it sounds like to me you're at least on par with existing technologies and existing lithium ion batteries, which are completely sufficient. 100, even 1,000 cycles in a 300-mile range EV. We're talking about probably longer than most people are going to drive that vehicle. So, totally sufficient. It sounds like.
Yeah, and typically, we're limited on the cathode side more than the anode side, and so, we're essentially at parity, I think, with the rest of the industry, depending on the design choices we make, and of course, the different cathode material choices have a big impact on that. So our consumer cells have significantly lower cycle life, as do almost all consumer cells, because they're using LCO chemistries, which are not as durable, but they're higher energy, and those are the trade-offs that that the end customer ultimately makes.
Let's go ahead and move kind of to the last topics that I want to talk about in this conversation, and that comes down to the commercialization of your battery cells. You're currently shipping batteries to suppliers, so you're actually manufacturing batteries and shipping them. Can you talk about those battery cells? I'm not sure if you can talk about what companies these are going to or not. Whatever you can share about that. And then I also want you to address something that we talked about before we started recording, and that's why are you currently making smaller batteries for electronic devices when maybe in the future you hope to be doing electric vehicle batteries? Like, why the small batteries now instead of
Yeah.
just jumping directly to EV batteries? So if you could talk about those two things.
Yeah, it's a great question, John. Thanks for bringing that up. So, let me address the second question first, which is if you're trying to develop an advanced battery, a next generation battery, and you believe in its ability to make a real difference in the electric vehicle space. And look, we started this company to go move the needle on EVs. We believe in that as the future of mobility. It's important for the planet, but it's also, we think, an amazing improvement in the driver experience, right? So we believe in all those things, and that's why we started the company. So why would you go into these other markets and work on cells that can really improve the performance of the devices that we use all day? And it really is a business model question. And we believe very strongly that new technologies typically you're better off introducing them to the market at the premium side, because by definition, a new technology is new. It means it's not at scale. It means it's more expensive in the short run because you haven't been working on it for 20 years getting the cost out. You're a new company, and so you don't have the same heritage and track record as, let's say, somebody who's been making auto parts for 50 or 100 years. All these factors, we think, make it very self-evident even that you should take your new technology into a market that absolutely can't even exist without it. Or the next level down is enable so much functionality in the end product, whether it's a smartwatch or a phone, that it's a massive competitive advantage for your customer to use your battery. And these are the things that allow you to overcome the hurdles of doing something that's new and different. And and it costs a little bit more in the early stages. And so that's been our strategy, and we've been extremely successful entering the market in the consumer side, mainly because energy density is a competitive weapon that allows people to develop products, mobile products, that have functions that couldn't exist because of power budget. And so therefore they're willing to take a chance on doing something new. And by the way, this is exactly the strategy that Tesla used to enter the EV space. They did not start with a low cost, economy car for the mass market. They started with the Roadster, which was incredibly expensive, but, so cool and so inspiring that, that a few people bought it, which then allowed them to go to a mass, a more mass market, but still extremely high-end car with the Model S. And they then worked their way down as they learned how to become a high quality and low cost and at scale manufacturer. They entered these larger volume markets. So we're trying to do the exact same thing. We've entered the market in consumer. Our first products are, wearable cells, which will be on the market with various devices, next year. We will likely be in more kind of mobile type devices the next year, and then laptop computers the year after. So we're in production. We have over 70 active programs with various consumer companies, including the who's who, kind of the big technology companies, and have we think are well along our way to a high quality business where we can make money and produce batteries, out of our own factories. And so given where we are on that market, it's allowed us now to go and start to make investments in the next phase of our market development, which is the electric vehicle space. We've launched an internal business unit called Enovix Mobility, which is busy designing a product specific for the EV space, but more based on our 3D architecture technology. And so there's a silicon anode component to that for energy density, but there's also a very specific focus on fast charge and the thermal properties we talked about.
Very cool. Well, Cameron, that's a bunch of exciting things that you just shared, and it sounds like your company is doing amazing things right now. It's exciting that you're shipping commercial products to customers. I'm excited of the potential of your technology for EVs and that you're working towards that. Is there anything that you want to share with my audience as we close this conversation? Anything that you'd like to talk about we didn't talk about, and where would you like my audience to either connect with you or connect with the company?
Sure. Yeah, John, thanks for the opportunity. This is a great, really fun conversation for me. And I really, really appreciate what you're doing with your show and your audience. I think it's, very high quality, and I'm a fan myself. So thanks for all that and having me on. I would just say, and this is harkens back to, the discussion we had before we turned on, but, it is not an easy journey to create a next generation battery product, but it is perhaps even a more difficult journey to get that product into manufacturing. And so one of the things we're the most proud of is shipping real commercial cells out of an automated factory, which has not been an easy thing to do. We built our factory during COVID, and so had to, work around those challenges. But here we are, and now we're at the beginning of what we think is going to be a really exciting ramp. People can certainly learn more about Enovics on our website. There's some pretty cool videos on, blowing up batteries and batteries that don't have the BrakeFlow technology. There's some cool videos of how our factory runs and some of the automated processes that we've developed to build the cell. So you can check us out there. I'm on LinkedIn. That's probably my primary social media platform, so people can look me up there, and happy to engage with people further on questions.
Wonderful. Thanks again, Cameron. And I'll definitely be following the company, and I look forward to all the exciting things in the future.
Great, John. Thanks.
Well, thank you so much for watching this video all the way through to the end. I'd like to take a moment to thank the Patreon supporters who support me every month and help make this content possible. A special thank you to my performance supporters and also the other supporters listed on the screen. If you'd like to find out more about the Patreon community I've set up, I'll put a link in the video description. Thank you so much.